Okay, so in chapter 20, we're going to talk about spontaneity and entropy of reactions. Okay, so let's talk about thermochemistry again, just to do a quick review. So the first law of thermo, what does it state? It states energy is conserved. So what does that mean? It means we can convert energy from one form to another, but we cannot create nor destroy energy. And we represented that by change in internal energy dealing with a delta E, where we said delta E was related to Q, which was heat, plus work, which was W. Okay. We also talked about delta H, which was a change in enthalpy, which related to just simply heats of these reactions. Now we're going to start talking about spontaneous processes and what determines whether a process is going to be spontaneous or not. So let's talk about what a spontaneous change is. Spontaneous change is something that's going to occur without having to continuously input energy from the surroundings, from outside the system. Okay? Spontaneous change is going to have a preferred direction. So what does this mean? Let's look at some examples. So if we look at water running downhill, we start with the water at the top of the hill. It's going to continuously run down the hill. We don't have to put any extra energy into it. Its preferred direction is running downhill. It's a spontaneous change. It's spontaneously going to run downhill. Right, now looking more at a chemical reaction side of things, we can also look at iron rusting in humid air. So if we put a piece of iron out in humid air, it's spontaneously going to start to rust over time. Okay, we don't have to put any extra energy into the system. It's just going to rust on its own. The preferred direction is going from the pure iron to the iron oxide, the rust. We can also consider what are called non-spontaneous changes or non-spontaneous processes. We can have a non-spontaneous change, but it means we have to provide a continuous supply of energy into the system. Now, if the process is spontaneous in one direction, it is non-spontaneous in the reverse direction. Simply because it's non-spontaneous in the reverse direction doesn't necessarily mean, though, that you can reverse the process. You can put a lot of energy into a non-reversible process and nothing's going to happen. Okay, so let's go back to our examples again. Water running uphill is a non-spontaneous change. It doesn't want to do it on its own, but we can put energy into the system to make that water run uphill. If we look at rust turning back into iron, okay, rust is not spontaneously going to change back into iron. Also, we can't easily change rust back into iron. Right? It's not as reversible as one would think. Okay, so in some processes we have a non-spontaneous change. We may not be able to reverse the process. All right, so let's go back to the spontaneous process again and see some things that affect that spontaneous process. So spontaneous processes are going to depend on temperature and enthalpy. So let's look at ice turning into water. Okay, that's going to be spontaneous at temperatures greater than 0 degrees Celsius. Okay, this is an endothermic process. Remember, endothermic, it's a positive, we're putting energy in. Okay, so it ends up being an endothermic process to go from ice turning into water. But it can happen spontaneously as long as we're at temperatures greater than 0 degrees Celsius. So if we look at water at less than 0 degrees Celsius, water turning to ice is going to be spontaneous. So at temperatures less than 0 degrees Celsius, we're going to go in the reverse direction shown here. That's an exothermic process because we're removing energy from the water to turn it into the ice, but that is spontaneous as long as we're below 0 degrees Celsius. So we can see with these processes, whether endothermic or exothermic, the direction we go, the spontaneous direction we go, can be dependent upon temperature. So what's going to occur exactly at 0 degrees Celsius, though? Well, at 0 degrees Celsius, if we're exactly at 0 degrees Celsius, we're going to have this equilibrium where we're going to have both the solid ice and the water present. Okay, if we put ice cubes in water and we cool that down to 0 degrees Celsius, as long as we don't go below 0 degrees Celsius, the ice would stay solid, the water would stay liquid. Now, as we just saw in the previous example, delta H does not predict spontaneous changes on its own. We can have a spontaneous change occur whether it's exothermic or endothermic. Like we saw in the previous example, ice melting is an endothermic process, but it can be spontaneous at certain temperatures. Water freezing is an exothermic process that can be spontaneous at certain temperatures. Okay? So let's look at some other examples of spontaneous exothermic processes. We can have like freezing and condensation at low temperatures. Those both involve removing energy from our system. We can have combustion reactions. Those are producing energy. We can have oxidation of iron and other metals. Those are all examples of spontaneous exothermic processes. Spontaneous endothermic processes are going to include things like melting and vaporization at higher temperatures. Okay, dissolving of most soluble salts, that's going to be an endothermic process. So what's the takeaway from all of this? Well, the sign of delta H does not by itself predict the direction of a spontaneous change. So delta H by itself cannot predict whether a process is going to be spontaneous or not. Okay, so there's some other factor that's going to be involved. Okay, so let's look at these two flasks here connected by the stopcock. One's evacuated, has a vacuum in it. The other one has 1 atmosphere of gas into it. When that stopcock is open, what do you predict is going to happen? Well, spontaneously, part of the gas from the B side of the flask is going to move into A. And that's going to be a spontaneous process. That occurs, and we can have that occur under any temperature, right? That's just going to occur. Okay? So why does this occur? Why does it go from one side to the other? Well, we're going to relate that to something called entropy. Entropy is another way we're going to identify whether a process is going to be spontaneous or not. So one thing to point out here, this process is spontaneous as shown. However, in this case, we're not going to reverse that process. Okay, the reverse process is not spontaneous, right? We're not going to have all the gas from A then suddenly move back into B on its own. It's not going to happen. So let's talk about entropy a little bit more. What is entropy? Well, a good way to think of entropy is just going to think about it's a measure of the possible distributions of energy. We need to think about something called microstates. So microstates are going to be these little possibilities of how energy is going to be distributed. Another thing we need to think about for entropy, it's going to be a state function. It's going to be independent of the path it takes. Spontaneous reactions, they're going to proceed to lower energy or higher entropy. Okay, so let's go back to these microstates. All right, what do we mean by microstates? Well, if we look at our flask again that's closed off by a stopcock, and let's say we just have 1 atom of gas on the left-hand side. When we open that stopcock, that atom of gas could be in the left-hand side, it could be in the right-hand side. Each one of those is a possibility. Each one of those possibilities is considered a microstate. Right, and we're going to call each one of those to be considered kind of a quantized energy state. Right, both of them are possible, and so A has a couple of options. The more options, the higher the entropy, because the more options means the higher number of microstates. Okay, and one thing to point out, you can see we have the microstates is going to be represented by a W, okay, an italicized W. So when we look at this, at any instance, the total energy of a system is going to be dispersed throughout one microstate. Each possibility represents one of those states, though. Okay? At any given set of conditions, each one of those states is going to have the same total energy as any other one. Therefore, each microstate has an equal chance to exist. So if we just look at one atom with two options, we can see that we go from that one condition to 2 microstates. What if we had 2 atoms? Well, now we have a wider variety of things. We still have 2 options for both A and B, but now because of the 2 atoms, we actually end up with 4 possible arrangements, 4 possible microstates. We could have A and B together on the left side, we could have A and B together on the right side, or we could have A on the left, B on the right, or B on the left and A on the right. Those are all possible ways of arranging A and B. So as we get to these larger number of possible microstates, there's a larger number of ways in which the system can disperse its energy, okay, which leads to a larger entropy. So if we go to A, B, and C, we can see that we go to 8 possible microstates, 8 possible arrangements of those. So we'd be able to disperse the energy of those 3 molecules across 8 different arrangements. Okay? The number of those microstates in a system is going to be related to entropy of the system through the equation S is equal to K natural log of W, where S is entropy, the W is going to be the microstate. K is a Boltzmann's constant. You don't need to worry about the value of K for calculations. I mean, it's a constant, so we'll give that to you. The main thing you need to recognize, though, is that S is going to be proportional to this W. So in looking at these 3 different sets of microstates, which one of those is going to have the highest entropy? Well, the highest entropy, if we go to 8 microstates, we plug that in, we'd have the highest entropy for the 8 microstates. The lowest would be the one with 2 microstates. Okay, so thinking in terms of entropy and how we're going to disperse energy, we're looking at options. What are the possibilities? What are the possible arrangements? The more possibilities we have, the higher the entropy. So let's look at some examples here and see if we can predict whether entropy is going to be increasing, decreasing, or staying the same. If I have a solid going to a liquid, what do you think is happening with the entropy? Okay, well, if I look at A on the left, which is the solid, and B on the right, which is the liquid, the system on the right actually is going to end up having more possibilities of arrangements because those molecules can move around more. So the entropy for the liquid is going to be greater than that of the solid. What about a liquid to a gas? Well, same principle as going from the solid to liquid. Liquid to gas, we're going to be increasing entropy. So the molecules are going to be able to start moving around more. So a key thing with entropy then is going to be dealing with freedom of motion. Okay, so we have the microstates. We also have the freedom of motion. Less freedom of particle motion, we have a lower entropy. Why? Because we have a localized energy of motion. The more freedom of particle motion we have a more dispersed energy of motion. Right? Remember, the more options we have for those microstates, for that energy to disperse across, the higher the entropy. Okay? So the more freedom of particle motion, the more possibilities we have, the larger the entropy. Okay, let's look at another example here. If I take solid sodium chloride and I dissolve it in water, I'm going to form Na plus Cl minus. Sodium chloride, what's its relative solubility in water? Well, table salt is going to readily dissolve in water. It's highly soluble. Going from that solid to the aqueous form, though, what is happening in terms of entropy? Are we increasing, decreasing, or staying the same? Well, I'm going from a pure solid, which is a sodium chloride, and a pure liquid, which is water, and when I mix them, I'm making up that solution. With that solution, because I have more particles in the end than I had in the beginning, I'm going to be increasing my entropy. So I'm going from NaCl, one particle, to an Na plus, which is aqueous, and a Cl minus, which is aqueous. So I'm going from one particle to 2 particles. Another thing to look at, though, too, is I'm going from a pure solid and a pure liquid into a solution. So just like a solid going to a liquid, that solid is breaking up, it's getting more particle motion, which means it has more freedom to move and disperse its energy in the solution. So I'm going to be increasing entropy when I go from a solid to a dissolved solid, or making those aqueous. What if I dissolve this liquid? Okay, well, if I look at the relative solubility of ethanol in water, ethanol is readily soluble in water as well. So there's got to be some driving force that allows this to occur. Now, I'm still going to form that liquid to the aqueous. It's similar in the way that I'm breaking apart the solid previously. So I'm going from a liquid to an aqueous, okay? The ethanol by itself in the liquid form is fairly structured. The water is fairly structured, okay? When I make a solution of the two, I'm increasing my entropy because now I've got more possibility of arrangements of how those molecules are interacting with each other, which means a more dispersal of energy, which means that higher entropy. So let's look at silver chloride solid. If it's going to dissolve into form Ag plus aqueous plus Cl minus aqueous. So what's the relative solubility of silver chloride in water? Well, if you look at a solubility chart, silver chloride is going to be listed as insoluble. Doesn't want to readily dissolve. Okay? Wants to mostly stay as a solid. But if we look at, similar to what we saw in NaCl, if we take that pure solid and that pure liquid and mix it to make a solution, we should be increasing entropy. But sodium chloride is highly soluble in water. Silver chloride is not so much soluble. So what's the difference from the sodium chloride? Well, one difference is because it's insoluble, we're going to be having it listed as an equilibrium, where not all of it's going to want to go into the aqueous phase. More of it's going to want to stay together as a solid. Okay? The interactions in the solid are going to be different because we have AgCl in one and NaCl in the other. So the attractive forces in the solid are going to help determine whether it's going to want to dissolve or not as well. So there's other factors that come into play. Not everything is going to be predictable simply by entropy. Okay. Let's look at another example here of a gas going to aqueous phase. So what's going to happen as we dissolve a gas? Are we going to increase, decrease, or stay the same with regards to entropy? So when thinking of a gas, you've got that large freedom of particle motion, which means we already have a large entropy. Right? When we go from the gas phase into the aqueous phase, we're actually going to decrease that energy because we're limiting the particle motion now. So when we take something in the gas phase and dissolve it, gas has a higher entropy than anything that's dissolved. So we're actually going to decrease that entropy. All right, so let's look at a couple more examples and just try to predict these. And we're going to try to predict what's happening as we go from reactant to product side. So here I have two aqueous particles going to a solid particle. What we'd expect to happen with entropy. Would it increase, decrease, or stay the same? So for this one, we have two aqueous particles going to one solid particle. So we're going from the aqueous form, which has more freedom of motion, to the solid form, which has less freedom of motion, so we'd expect this entropy to be decreasing. Okay. What about CH4 to aqueous to CH4 gas? Well, we're going from the aqueous form to the gas form. The gas form actually has more freedom of motion, and because we only have one particle and one particle, we'd expect entropy to be increasing as we go from aqueous to gas. All right, what about this one? So we have HCl aqueous, NaOH aqueous, going to NaCl aqueous, and H2O liquid. Well, we have two particles on the left, two particles on the right. Two on the left are both aqueous. On the right, we have one aqueous, one liquid. The aqueous has more freedom of particle motion, so therefore, in this case, as we go from reactants to products, we'd be decreasing entropy because that water is in liquid form, which means we have less freedom of motion. Okay, so remember, with entropy, we have to deal with freedom of particle motion. That less freedom of particle motion, we get a more localized energy. More freedom, we get dispersal of that energy, which means more microstates. Okay. Now, let's look at another this is a graphical example where we have fraction of particles versus kinetic energy. Okay, kinetic energy, keep in mind, is that energy of motion. So as I start with this example here, or this graph showing certain particles having a certain amount of kinetic energy, or an average amount of kinetic energy. As I add heat to it, what happens? Well, the average kinetic energy starts to increase, right? And where we see the average is where we have those peaks. Okay. So as we add heat, we're adding more energy. So what does this mean? Well, on the left-hand side, we have a lower temperature, which means fewer microstates, which means a lower entropy value. On the right, we have a higher temperature, which means more microstates, which means a higher entropy value. So as we add heat and increase that temperature, we're going to increase entropy. Okay. Now, another thing we can look at is a change in the number of gas molecules in a reaction as a way to predict entropy. So as I go from ammonium chloride solid to ammonia gas and HCl gas, I'm going from that solid to 2 gas particles. Okay, well, the 2 gas particles have more freedom of movement, definitely because they're gases versus solids, so therefore we'd expect them to have higher entropy, so we'd expect to be increasing entropy in this case. Okay, so let's look at this one. I'm going from 2 gas particles on the left to 2 gas particles on the right. Yes, they've kind of changed how they've connected and the bonds they've made, but if I look solely at the number of gas molecules, 2 on the left, 2 on the right, I'd expect entropy to stay the same because I'm not changing the number of particles. Okay, if I look at this next one, I've got 2 particles on the left, I've got 4 particles on the right. So I would expect, because of the 4 particles, those would have a higher entropy. So I'd expect entropy to be increasing on this one as I go from left to right. Okay, so number of particles are going to affect entropy, and this goes back to what we were saying in the example with the microstates, right? If I have 1 particle, A, I have 2 microstates. If I have A and B, I have 4. If I have A, B, and C, I have 8. As I go to higher number of particles in the gas phase, I get a higher number of possibilities, a higher number of microstates. Okay, this is kind of removing out, though, any phase changes. So we're talking more about if they're all in the gas phase. Okay, another thing that can affect entropy, especially dealing with gases, is the pressure of the gas at constant temperature. If I take hydrogen gas at 1 atmosphere and increase the hydrogen gas to 2 atmospheres, what's going to happen to entropy? Well, maybe an easier way to look at this is in this picture here. On the left, we've got the pressure of the gas at 1 atmosphere. On the right, we've got the pressure of the gas at 2 atmospheres. So between those, which one has more freedom of motion? Well, the one on the left, the particles can move around a lot more. They have more freedom. Therefore, as we increase pressure, we decrease that freedom of motion, which means we decrease entropy. So in this case, going from 1 atmosphere to 2 atmospheres is decreasing entropy. And along with pressure, we can also look at the volume difference, where we have 1 liter versus half a liter. Okay, if you remember PV equals nRT, don't forget your ideal gas law, pressure and volume are related. As long as we keep the same number of moles of a gas, that volume is going to decrease if we increase pressure, and therefore we get that less freedom of motion because we have a smaller volume. Alright, let's look at some other things that can be affected by entropy or help predict entropy, one of which is atomic size. Okay, if we look at these group 1 elements and we look at their atomic radius, we can see that as atomic radius increases, what's happening to the entropy? As atomic radius increases, entropy is increasing. Okay. Now, another factor along with that is if we look at molar mass of each one of those, as molar mass increases, entropy increases. If we look at these compounds, HF, HCl, HBr, HI, we can see that molar mass is increasing, which also means the entropy is increasing. But if we look at the size of those molecules, HI is going to be larger than HF because the iodine is going to have a larger radius than the fluorine. Okay, so if we strictly look at atomic size, As we go, atomic radius goes up, entropy goes up. So why is that happening? Well, it turns out that the energy levels within an atom get closer and closer together as we get to larger atoms. Because of that, we actually get more microstates, which means an increase in entropy. So another thing I can look at is structure. So structure of these compounds or materials. If I look at carbon in its graphite form versus carbon in its diamond form, carbon in the graphite form has a higher entropy than in the diamond form. Okay, if you think about it, graphite is arranged in these sheets that allow these molecules to move past each other. That's why we use it to write with. Whereas diamond, the carbon atoms are more bound together, which is why diamonds are harder than graphite. So in the graphite, these atoms have more freedom of movement, which means they're going to have more possible microstates, which means they're going to have a higher entropy. Now, structure-wise, we can only look at structure as long as these substances are in the same physical state. So in both instances here, carbon is in a solid form. We can't look at the structure of carbon diamond and try to compare that to carbon in, let's say, the gas phase. That's a phase change, not a structure. Okay, the gas is always going to have more entropy than anything in the solid form. That's the same compound. Now, another aspect of structure, though, is this isn't within the same compound. These are different compounds. So what are we seeing here? As I go from NaCl to AlCl3 to P4O10, I'm seeing an increase in entropy. Likewise, as I go from NO to NO2 to N2O4, I get an increase in entropy. Why is that happening? Well, I'm getting to more complex molecules. As I go to more complex compounds, I get a larger amount of microstates possible for their energy levels. Therefore, I get a higher entropy. So the more complex the compound, the more entropy I'm going to have. Another way to look at it is simply, how many of things do I have? If I look at the NO versus the N2O4, well, the NO has 1 nitrogen, 1 oxygen. The N2O4 has 2 nitrogens, 4 oxygens. I've got more atoms in that compound, so I'm going to have more entropy. So the more complex a compound gets, the higher its entropy is going to be. Okay? Again, this is dealing with structure only in the same physical state. I can't compare liquid sodium chloride to gaseous NO. Okay? These all have to be in the same state. That's why the NaCl, AlCl3, and P4O10 are compared as solids, whereas the NO, NO2, and N2O4 are compared as gases. Okay? So let's review a little bit here as to what entropy depends on. Entropy depends on temperature. Okay, so for any substance, entropy is going to increase as temperature increases. Entropy is going to depend on the physical state. So entropy is going to increase as the phase changes from solid to liquid to gas. The formation of a solution affects entropy. If I go from a solid to a solution phase, I'm going to get an increase in entropy. If I go from a gas to a solution phase, in other words, I dissolve a gas, I'm going to decrease entropy. Okay? Pressure of a gas is going to affect entropy. Higher the pressure, the lower the entropy. Okay? Entropy is also going to be related to atomic size and molecular complexity. Okay? With that, though, we have to remember to compare substances in the same physical state. So as I increase size, I get a higher entropy. As I get a higher amount of molecular complexity, I get a higher entropy.